if x naught is a point of extremum with those restrictions, then there exists a vector lambda naught of Lagrange multipliers such that the Lagrange function x1 so on xn lambda 1 so on lambda m, which is f x1 so on xm plus xn plus lambda 1 phi 1 x1 so on xn plus so on plus lambda m phi m x1 so on xn. For this Lagrange function, the point x naught lambda naught is a critical point. So that is the assertion of theorem 3. And how we proceeded? We deduce that from the fact that this determinant is not 0, then we can express variables x1 so on xm. So 1 is equivalent to x j equals to psi j of x m plus 1 so on xn, j from 1 up to m, and that is 1 prime. That is 1 prime. And after that, the problem to find the extremum with constraints is equivalent to the problem of usual extremum for the function capital F, which can be represented as follows. That is f of variables psi 1 xm plus 1 so on xn so on up to psi m. So the first m variable we express in terms of other variables. That is the idea. So we replace the problem to find relative extremum with constraints by the problem to find usual extremum. Of course, that is valid only when we are in a small neighborhood of this point x naught. And then also I'll need some further so what we did, we started to study this problem, and it was necessary to look at the differential at a point x naught tilde, that is df x m plus 1 naught so on x n naught, and because of, you see, if we look at the function capital F, then we recognize the function small f where we substitute variables x1 so on xn, and because of invariant of the first differential, this coincides with differential f at x naught without tilde, and that is the sum of partial derivatives x naught times dxj. And necessary condition for the extremum problem here is that this should be 0, and that was condition 2. And also we recognize that if we differentiate the condition 1, then we obtain, so differentiating constraints, we obtain the system of equalities for differentials. So differentials of phi j's should be 0. Okay, let me write. And here, in fact, we can choose arbitrary point. So when we choose arbitrary point which satisfy restrictions 1, then we can differentiate those functions, and these are zeros, j from 1 up to m. These are conditions 3, and of course, since conditions 1 are equivalent to 1 prime, then we can differentiate 1 prime as well, and it gives that differentials of xj's are equal to let me recall what is 3 prime. Yeah, just d psi j. D psi j of x tilde. And in fact, it seems I wrote it only, I wrote it only for the point x naught. So that is 3 for the point x naught, and here also x tilde naught, and these are 3 prime. Okay. So that is what was done during the former lecture, review of the former lecture. So we stopped, I think, just on the system 3 prime. We stopped, right? Yeah. Okay, so let me rewrite the system 3. So here we have some differentials, right? So we can rewrite them as sum k from 1 up to n, partial derivatives phi j with respect to x k at x naught times dxk equals to 0. J from 1 up to m. Okay, then let us multiply those equalities by lambda j's, j from 1 up to m respectively. So we have a system of equalities, right? And then we multiply them by lambda j's. and add them to 2. I think the index is not good. Maybe I'll change the index in 2. Let me change the index in 2 by 2k. Instead of j, it's better to write k as the index for 2. Okay, so what I do? We have m equations here. I multiply each of them by lambda j, right? And then sum up them and add also 2 all together. So what we obtain? Then we'll obtain, so sum up with 2. Then we obtain sum k from 1 up to n, and let me rewrite everything. So df over dxk at x naught plus lambda 1 d phi 1 with respect to xk at x naught plus so on plus lambda m d phi m over dxk at x naught, and that is a common multiplier in dxk, and the right hand side everywhere is 0. So when we sum up zeros, we obtain still 0. So that is what we obtain by summing up everything. And then you recognize what is in brackets. What is in brackets is precisely Lagrange function. Or better to say, not Lagrange function itself, but its derivative with respect to xk, right? So what remains is that one. Partial derivative of L, Lagrange function, and okay, Lagrange function depends on variables x's and also lambdas. So x0 here and also lambda vector. That is dxk should be 0. Okay, now let us choose lambda k's, k, lambda j's, but j's, j from 1 up to m, such that partial derivatives with respect to x k's should be equal to 0 for k from 1 up to m. M, not n. Here we have n derivatives, and we choose only first m partial derivative. We want to choose such lambdas that is 0. Okay, I think I should put some number here. Oh yeah, numbers are, that is 4, and the system, yeah, that is 5. Yeah. Okay. So let us think about what means to solve 5 is a system of equations, right? Look at the partial derivatives. Here they are written. And let me rewrite. So 5 is nothing else but we have the following system. So lambda 1 d phi 1 with respect to dxk at x naught plus so on plus lambda m times partial derivative of phi m with respect to dxk at x naught should be equal to minus partial derivative of f with respect to dxk at x naught k from 1 up to m. That is 5 prime. So I rewrote 5 explicitly, and then you see what is 5 prime. 5 prime is a system of linear equations. We have m linear equations with m unknowns, lambda 1 up to lambda m, right? And what is determinant of that system? So determinant of 5 prime is that one, right? That Jacobian, precisely. So determinant of 5 prime is our Jacobian. At x naught, which is not 0 by our supposition, right? So it means we can find for sure unique. So hence there exists unique solution of 5 prime lambda I'll denote by lambda naught, right? That is the unique solution of 5 prime. So we solve the linear system 5 prime. The determinant is not 0. We obtain unique solution, a vector of variables lambda 1 naught so on, right? So lambda 1 naught so on lambda m naught. Okay. Now if we substitute this vector of lambdas into 4, then what we obtain? So substitute lambda equals to lambda naught into 4. Then what we obtain? What remains? You see, 5 prime is equivalent to 5, right? And it means the first m terms here, m coefficients, are zeros, right? So it gives, as a result, we obtain the following: x naught lambda naught dxk equals to 0. But now look, what is it? That is equal to 0 for arbitrary dxk, right? But remember that our variables xn plus 1 up to xn are independent, right? Because when we solved, we observed that here variables are independent, xn plus 1 up to xn. Hence, if this is identically 0 for arbitrary dxk, then because of dxn plus 1 so on dxn are independent, or maybe without xn plus 1 so on xn are independent variables. Hence we deduce that all partial derivatives are zeros, k from m plus 1 up to n. Then look, so lambda naught satisfy 5, right? So partial derivative dl with respect to xk are zeros for k from 1 up to m, right? So for k from m plus 1 up to n also we have this. And lastly, what are derivatives of L with respect to lambdas? If we differentiate the function L with respect to lambda, then we have precisely phi, right? The function phi. So that is phi k at x naught, and that is 0, because x naught satisfies the system of constraints, right? And what it means? All partial derivatives of our Lagrange functions are zeros. It means the theorem is proved because of what we did. We proved that there exists a unique lambda naught, right, such that x naught lambda naught is a critical point of the Lagrange function. And that is what we wanted to prove. So theorem is proved. Theorem is proved. Now what is about sufficient condition? As we know, for sufficient condition, we need to consider second differential, right? So, what is second differential? And let me denote. So, notation. We denote by d2l xx is the second differential of the Lagrange function in the supposition of fixed multipliers lambda. So what it means? In general, we have Lagrange function is a function of variables x and lambdas, right? So if we want to write second differential, then we should write all partial derivatives of second order with respect to variables x, mixed x and lambdas, and okay, if you differentiate twice with respect to variable lambda, then you obtain 0, right? So second derivatives with respect to lambdas are zeros, but nevertheless second derivatives with respect to lambdas and x's are not zeros. That means that in general, this second differential, if we forget about it, it will contain more terms. But, as I said, we fix multipliers, so we forget about function of lambdas. So you see, lambdas are fixed, right? We look at the Lagrange function as a function of variables x only. Don't change lambdas. Lambdas are fixed. So that is the notation. And then also consider d2l xx as a quadratic form of variables dx1 so on up to dxn, which satisfy the conditions, maybe without them, conditions, so where this number 3 prime or 3 doesn't matter, conditions 3. Conditions 3. What are 3? 3, what they are? Look at 3. We differentiate restrictions. So we consider restrictions, we differentiate them, and it gives a system of equations for dx1 so on up to dxn. Relations between those dx1 so on dxn. In fact, these are linear relations. And we have to consider our quadratic form as a quadratic form of variables. So in fact, that is not a quadratic form of variables dx1 so on up to dxn, and that is a quadratic form of variables dxk k from n plus 1 up to n only, because other variables dx1 so on up to dxm can be represented by 3 prime in terms of dxm plus 1 so on up to dxn. So we should to consider quadratic form of smaller amount of variables, not of n, but of n minus m. That is the point. Okay, now I can formulate theorem 4. Yeah, theorem 4. Sufficient conditions for relative extremum with constraints. Suppose f is continuously twice differentiable in a neighborhood, I'm always mixing with this neighborhood, it seems like that, in a neighborhood of x naught, neighborhood of x naught, x naught satisfies constraints 1, the Jacobian matrix partial derivative of phi 1 with respect to x1, phi 1 with respect to xn, phi m with respect to x1 phi m with respect to xn at x naught has rank has maximal rank m less than n, right? And x naught lambda naught is a critical point of the Lagrange function L of x lambda. Okay. If second differential xxl at x naught lambda naught is a positive or negative definite quadratic form of variables dx1 so on dxn under the supposition three, then x naught is a strict minimum maximum point of f with constraints 1. If d2 xx l x naught lambda naught is indefinite form with the same suppositions then x naught is not an extremum point of f with constraints 3. Oh, sorry, 1. Constraints 1. Now proof of theorem 4. So for proof, first of all, let me recall that during the proof of theorem 3, we observed that the extremum problem which we studied, so the extremum problem the extremum problem with constraints one is equivalent to the local extremum problem for capital F of x m plus 1 so on xn. Of course, that is true only under this extra supposition. So remember, we have the supposition about maximal rank of this matrix, and we have extra supposition, that is without loss of generality. We suppose once again that this determinant is not 0. Okay, then so we want to solve usual local extremum problem. As we know, we have differential, which is, yeah, it was written here, equations 2, differential, which coincides with differential f at x naught, and in fact, if we substitute our function L, then remember that we deduced system 4 for lambda naught, so that is differential of L. Let me indicate that only with respect to variables x, and also at the vector lambda naught, that is 0. So this was obtained during the proof of theorem 3. So x naught lambda naught is a critical point of the Lagrange function. Okay, now let me rewrite the differential where it is written. Yeah, so differential f at arbitrary point x tilde in our neighborhood. It was written in system 2, but now I don't need to consider the point x naught, so I need to vary the point, so it gives the following equality: df with respect to xk at x vector dxk. That need not to be 0, but the point that to study, so if we want to solve the extremum problem, then we need to study the second differential of the function capital F. So what is second differential? And of course, at the point x naught, since we look at the possibility of the extremum of the function capital F, then we need to consider second differential at the point x naught. So what is it? We need to take differential. And now remember that yeah, so so I need to replace now the function f by the Lagrange function. So in fact, you see that yeah, we choose lambda naught in such a way that no, in fact, the system 4 was obtained for arbitrary lambdas, right? So it means that here I can replace by the Lagrange function. Why? Because we add zeros. So remember the proof of theorem 3, how we obtained the system 4, right? And in fact, instead of x naught, we can replace by arbitrary point x, which satisfy the constraints 1, because what we did, we added 3 multiplied by lambda j's, and 3 were differentiated equations 1. So once 1 are satisfied, we can differentiate and we can replace partial derivative of f by partial derivative of L. That is precisely dL, but with respect to variables x only, at x. Okay, then, so I want to find second differential. It means I need to take differential of the first differential, so I need to differentiate this expression. Then what is it? That is sum j from 1 up to n, sum k from 1 up to n. So firstly, I differentiate this expression. It gives second partial derivatives of L with respect to xj, xk of, yeah, now at the point x naught times dxj dxk plus the sum k from 1 up to n dl over dxk at x naught times second differentials of xk. So I took second differential of our expression, But remember that, yeah, in fact, here I should add also lambdas, because let me insert here lambdas, right? Because also our Lagrange function depends also on lambdas, so I should insert here lambda knots, also here lambda knots. But now remember that by theorem 3, x naught lambda naught is critical point, right, of the Lagrange function. hence these are zeros. So this is absent, right? And also when we consider second differential of capital F, remember that how we obtain the function f. Function f is obtained when variables xj's are replaced by psi j's. So it means 1 prime is satisfied, right? 1 prime is equivalent to 1, and it means that variables dx1 up to dxn are not independent. They are connected by equations 3, differentiated constraints, right? So you see that here dx k's, k from 1 up to n, satisfy 3. And now it completes the proof, because look, what is written is precisely that one, right? Second differential of the function L, if we forget about lambdas, right? And also variables dxk satisfy differentiated conditions. And now look, what is written here is precisely sufficient condition of the extremum for capital F, right? So if this is positive, then second differential of capital F is positive, hence the function capital F has strict local minimum, and if capital F has strict local minimum, then the original little f has relative strict minimum with constraints, and other parts are in an analogous way, right? So we just reformulate our problem for capital F in terms of the problem for little f, and the theorem is proved. Okay, now I want to consider a couple of examples. So let me erase everything. So I reformulated the sufficient condition in terms of, so you need to consider second differential with variables which are connected by this system 3, right? In fact, you can rewrite in terms of so-called bordered Hessian, but I don't want to do it. It's quite equivalent, and it seems to me this is more transparent when you understand how it is obtained. Although maybe technically it's simpler just to consider that bordered Hessian. So example 1, we have function f of x y equals to 1 minus 4x minus 8y, and restriction constraint is phi1 of xy is equal to x squared minus 8y squared minus 8. In other words, we want to solve the extremum problem for linear function when x and y satisfy this equation. So it means not equation. Equation is x squared minus 8 squared equals to 8. That is an equation for hyperbola, right? So, okay, how to solve? We consider the Lagrange function. Only one Lagrange multiplier, since we have only one constraint, and I'll omit index 1, just lambda. So what is it? We need to take our function. Okay, let me rewrite it explicitly, right? Plus lambda times constraint. That is the Lagrange function. And then first of all, we need to find critical points. So to find critical points, we take partial derivatives. That is minus 4 plus 2 lambda x. And with respect to y, it's minus 8 minus 16 lambda y. And lastly, partial derivative with respect to the Lagrange multiplier is precisely our constraint. I mean, when we want to find critical points, we should equalize everything to zeros, right? So it gives the system of equations, and you see this is a nonlinear system, right? With respect to x, y, and lambda. We have three equations, but they are nonlinear. Nevertheless, here it is not very complicated, so we deduce that x equals to 2 over lambda, right? Here we deduce y equals to minus 1 over 2 lambda. And when we substitute, we have 4 over lambda squared minus 8 over 4 lambda squared minus 8 equals to 0. It gives 4 minus 2, so 2 over lambda squared equals to 8. Lambda squared equals to 4 over 4, right? So lambda plus minus 1/2, and hence we have two critical points. So critical points of the Lagrange function, critical points, we have two of them. So 2 over 1/2 gives 4, and minus 1, y is minus 1, right? If we substitute lambda is 1/2, lambda is 1/2, and minus 1/2 gives minus 4, 1 minus 1/2. So we have two critical points of the Lagrange function. After that, we need to consider second differential. So what is it? Let me firstly write at arbitrary point. So what is it? Remember that we forget about lambda at the moment, right? So when we need to consider second differential, we forget about lambda. We fix lambda, right? So it means that standard form for second differential is that one, d2 over dx twice dx squared plus 2 d2l over dx dy dx dy plus second derivative with respect to y twice dy squared. That is in general, not at the critical point, just at an arbitrary point. Okay, so second derivative with respect to x, remember here we wrote derivative, differentiate with respect to x, we obtain 2 lambdas, right? So 2 lambda dx squared. Then if we differentiate this derivative with respect to y, we obtain 0. So if we differentiate derivative with respect to y, we obtain minus 16 lambda. So minus 16 lambda dy squared. Okay, so also we need to remember that dx and dy are not independent, right? They should satisfy differentiated restriction. So we have constraint like here, right? And we differentiate it. So if we differentiate, what it means? We take differential. So what we obtain? 2x dx minus 16 y dy equals to 0. So it gives that, for example, dy, or maybe dx, it's easier, dx equals to 8y over x dy. That is the connection between dx and dy. So it means that we need to consider not this differential, right? But the differential when we substitute this relation between dx and dy. And it gives what it gives. Take square, so 64, 128 lambda y over x dy squared minus 16 lambda dy squared. Or, okay, maybe I'll put 16 as a common multiplier. So 2 power 4, that is 2 power 7. So 8 lambda y over x minus lambda, maybe lambda also, minus 1 lambda dy squared. That is our second differential when we substitute, right? Now we look at critical points. So 4 minus 1, 1/2. What it gives to us? X is 4, y is minus 1, so 16 times minus 8 over 4 minus 1 times 1/2 dy squared. That is minus 2 minus 3 times 8, so minus 24 dy squared. Negative definite. Negative definite. Negative definite. So it means that that is 4 minus 1 is a maximum point. Maximum point. F of 4 minus 1, which is 1 minus 16 plus 8, right? So 9 minus 16 minus 7 is maximum. Now look at minus 4, 1, minus 1 half. Here we obtain 16 times. So y is 1, x is minus 4. So 8 over minus 4 minus 1 times minus 1 half dy squared. That is still minus 3, but now plus, so 24 dy squared. That is positive definite. Positive definite. Hence, the point minus 4, 1 is a minimum point. In fact, strict minimum, but doesn't matter. Minimum point. And f of minus 4, 1 equals to, if we substitute minus 4, so 16, 17 minus 8, that is 9. Minimum. Yeah. Okay. Okay, so yeah, in fact, it seems a little bit strange that maximum is less than minimum, right? Why? Because in fact, what we have here hyperbola, right? And hyperbola has two branches, two different branches, right? Which are separated from each other. And you see that one point lies on one branch, another point on another branch. So it means that our linear function for one branch has only maximum, and for another branch has only minimum. No other extreme. That is why it seems firstly surprising that minimum is greater than maximum, but it happens quite often, especially when we have such a picture of non-connected domain. Okay, so we have 10 minutes. I have one extra example. Example 2. That is an example of example 2 of a not a local but global extremum. Global extremum, right? So the problem is to find maximum and minimum, not a local, not a relative, but global. So, absolute. Maximum and minimum of u equals to x squared plus 2y squared plus 3z squared, subject to x squared plus y squared plus z squared equals to 1, x plus 2y plus 3z equals to 0. So we have two restrictions. What is question?
We're replacing the or b is squared, but y, the variables x, y are squared. There in 1 second. The second.
Yes. Yes, I forget. Thanks a lot. I think, but it most probably didn't change. Thank you very much. Yes, thank you. Thank you. What it changes? It's always with plus then. 8 y squared is 1, x squared is 16, right? 16. So 1/2 minus 1 minus 1/2 minus 1/4 minus 4. Yeah. And if we replace here, that is still 8 over 16. And it gives 1/2 minus 1/2. Now it's plus 4, right? Yeah. Yeah. Thank you. Yeah. Although the conclusion is the same, right? Fortunately. Thank you very much. Yeah, I forget. I did that equals to 6z plus 2 lambda z plus 3 mu. Okay. Then look. We need to, okay, I forget to write also. The L over d lambda equals to x squared plus y squared plus z squared minus 1 should be 0. And the L over d mu, which is x plus 2y plus 3z, should be also equals to 0. Okay, so to find critical points, we need to equalize to 0, right? Everything. You see, we have a system. Chart is for you. Okay, so look, we need to solve that system of equations. But in fact, we don't need to solve it. That is a rare case because the question is to find maximum and minimum, not to find maximum and minimum points. We need to find values of the function where it is, when it is maximal or minimal. When. We don't need, there is no question for which values of x, y, and z the function has maximum. We need only to find the maximum. Okay, so then look, multiply by x, this is by y, that is by z, and add. What we obtain? Look, here we have 2x squared plus 4y squared plus 6z squared, right? If we add those three. Then plus 2 lambda times x squared plus y squared plus z squared plus mu times x plus 2y plus 3z. And you see, that is 1, right? That is 0 by our restrictions, and that is 2 times u. So you see that at a critical point 2u plus 2 lambda equals to 0. So for an arbitrary critical point, we have such an equation, or u equals to minus lambda. What it means? It means that to find maximum and minimum, we need only to find lambdas. We don't need to find x or y or z. To find maximum, we need to find lambdas only. Once we know lambda, then we can find maximum. Okay, let's have a break. And next lecture, I'll need to finish this example. Thanks for your attention and for your good remark.